The NHERI experimental facility at the University of California, San Diego will provide large-scale, high-performance experimental infrastructure to advance the science and practice of natural hazards engineering and to educate the future generation of engineers. Only 10 miles east of the UC San Diego campus and only 16 miles northeast of San Diego International Airport, NHERI at UC San Diego is easily accessible to researchers and educators from around the world. Research conducted at the NHERI at UC San Diego experimental facility will lead to improved design codes and construction standards, validated computational simulation models, and accurate decision-making tools necessary to build and maintain sustainable and disaster-resilient communities. To accomplish this, UC San Diego will provide 2 world-class, one-of-a-kind facilities to the NHERI network. The first is the large, high-performance outdoor shake table, referred to as LH Post, which was developed under the NSF NEAS program. The LH Post enables real-time dynamic testing of large to full-scale structural and non-structural systems to understand the performance of buildings, critical facilities, and bridges. It can also accommodate large soil boxes to investigate soil structure interaction problems. The platen, which is the part of the shake table that moves, is surrounded by a reinforced concrete reaction mass. Installed here on the table is a full-scale electrical substation consisting of poles and insulators, some of which are equipped with spring dampers at the base supporting 500 kilovolt transmission lines. NHERI at UC San Diego will also make available a California Department of Transportation-funded Soil Structure Interaction Facility, referred to as the SSI facility, consisting of 2 large refillable soil pits separated by a reaction wall. Other features of the NHERI facility include a hydraulic power and control system building, construction support equipment, meeting and office space, and a machine shop. The facility provides extensive space for construction and ease of access. Heavy test specimens relative to the table's 2,000-ton payload capacity are built directly on the platen. As a Year 1 upgrade to the facility, the construction of a heavy-duty staging area has been proposed to maximize the shake table's throughput. Small to moderate-sized specimens weighing up to 100 tons would be constructed on the staging area and then lifted onto the LH Post. The hydraulic power system is shared by all test equipment at the NHERI site. It consists of 2 hydraulic pumps, a surge tank, an accumulator bank, a pressure regulating valve, and a hydraulic piping system. A cooling tower and electrical power substation are located outside the building. A service tunnel connects the hydraulic power and control system building to the LH Post. Under the table, surrounded by the reinforced concrete reaction mass, one can see the infrastructure that supports the 25 by 40-foot honeycomb steel platen. The LH Post is driven in its longitudinal direction by a set of 2 servo-controlled dynamic horizontal actuators, one at each end of the platen. During testing, the shake table slides over 6 vertical actuators, currently used as active hydrostatic bearings. 2 nitrogen-filled struts connected to the bottom of the reaction mass compress the platen against the vertical bearings to control overturning of the platen by the sway of the specimen. The LH Post currently performs as a single-axis shake table. However, the facility was built for easy upgrade to 6 degrees of freedom. Upgrading to this capacity will not require any structural modifications, but only the acquisition of additional servo-hydraulic equipment. In its current single degree of freedom configuration, the performance specifications of the LH Post are significantly higher than any other shake table in the United States. Of the 25 research projects performed on the LH Post thus far, only 2 could have been performed on the second largest shake table in the U.S. Furthermore, at least 4 projects could not have been performed on the largest shake table in the world in Japan due to height restrictions. Because of its full-scale, system-level dynamic testing capabilities, use of the LH Post circumvents the problems related to inaccurate boundary conditions and scaling. An additional distinguishing feature is its payload capacity of 2,000 tons, allowing the LH Post to be used in combination with large soil boxes. This enables the seismic testing of geotechnical systems, such as underground structures, bridge abutments, and earth retaining walls. The heaviest specimen tested on the LH post thus far weighed 1,000 tons, representing only half of the table payload capacity. The LH post is particularly useful for conducting tests of components and systems at large or at full scale when material constitutive relationships show sensitivity to size or strain rate effects, or when off-the-shelf commercial products are incorporated as primary components in the test. In this test, 2 bridge columns seen from the top of the large confinement soil box are responding to an earthquake by having their footings rock on the soil compacted inside the soil box. The soil box was outfitted with a bladder, and water was added to the soil to simulate realistic conditions where the water table sits just below the foundation of a structure. This test of a retaining wall with soil backfill performed in a laminar soil shear box allowed researchers to investigate the soil failure mechanism behind the wall at full scale. This half-scale landmark experiment tested a 4-story building specimen equipped with an innovative floor anchorage system that reduced the inertial forces during an earthquake, minimizing structural damage and maintaining a plumb, vertical configuration of the building at the end of the earthquake. This seismic test of a half-scale precast concrete parking garage investigated the complex system behavioral modes of precast concrete building structures and especially their floor diaphragms. This allowed for the development of high-fidelity nonlinear finite element models, which were used to develop seismic design provisions that will be incorporated in the 2016 edition of the ASCE 7 standards. This experiment also illustrates the possibility of testing structural specimens with a footprint significantly larger than the size of the shake table platen, using outrigger arms sliding on low-friction bearings. This test of a wind turbine standing over 100 feet tall demonstrates how this outdoor facility with no overhead height limitations enables the testing of taller specimens than is possible on any other shake table in the U.S. and the world. This full-scale 4-story wood frame building provided a system-level test to validate the effectiveness of building evaluation and retrofit techniques that are currently being implemented in more than 6,000 buildings as part of San Francisco's mandatory soft-story retrofit program. Because of the unique capabilities that the LH post and SSI facilities offer, strong industry engagement is typical of many test programs at the facility. The involvement of practicing engineers and code-writing committees who play a key role in using and disseminating the research findings to industry will transform the state of practice. The impact of NHERI at UC San Diego will extend beyond engineering practice. We will provide enhanced outreach activities in an effort to recruit K-12 students from diverse backgrounds into STEM fields. The research, education, and community outreach plans at NHERI at UC San Diego experimental facilities will ensure that NHERI will play a significant role in educating the next generation of structural engineers, with special emphasis on characterization and mitigation of natural hazards such as earthquakes, hurricanes, and tornadoes.